Let's talk about parent functions. In grade 11, we talked about a number of parent functions, and it's important in this part of the course for you to know those parent functions, at least at first, their basic behaviors. So let's consider the square root function y equals root x. In grade 11, you learned that there are certain key points on that curve, and the curve looks like this. It's essentially 1/2 of a sideways parabola. You should remember the essential behavior of the function as well as these 3 points that I have listed in red, 0, 0, 1, 1, and 4, 2. The domain of this function is x element of the real such that x is greater than or equal to 0, and the range is y element of the real such that y is greater than or equal to 0. The increasing intervals of this function is x element of the real such that x is greater than or equal to 0, or x is an element of 0 to infinity. 0 has a square bracket, infinity has a round bracket. Generally speaking, when we do intervals of increase or decrease, we put them in interval notation. That's the usual way. Decreasing intervals, there are none. The function is not even, because if it was even, then it would reflect on itself, which it clearly doesn't. And the function is not odd, because if we rotate it 180 degrees about the origin, it does not fall back onto itself. There is no end behavior as x goes to negative infinity. So this is one of those rare cases where when we ask for end behavior, you can only really state it in one direction. As x goes to infinity, y goes to infinity. The curve will become infinitely high and the y values will become infinitely large as x goes to infinity. Now let's talk about the absolute value function. Remember that the absolute value of a number is the distance of that number from 0. And we show we're evaluating the absolute value by putting the number inside absolute value bars. In other words, we show we're evaluating the absolute value of 6 by writing 6 in those absolute value bars. So for example, the absolute value of 8 is 8 because 8 is 8 units from 0. Imagine a number line. There's 0 and there's the number 8. Well, 8 is 8 units away from 0. And similarly, the absolute value of negative 8 is 8, because if you look at negative 8 on that same number line, it is also 8 units away from 0. Now let's make a table of values of the function y equals absolute value of x. We see that we get these points. And when we graph those points and recall the behavior of the function, it looks like this. It's important when you ultimately graph this function with transformations to recall the basic behavior of the function and recall the 3 points that we've listed right there. The domain is all real numbers. In other words, there is no real number that you cannot put in for the number x, for the variable x right there. The range, as you can see from the graph, is all values of y greater than or equal to 0. Now, the increasing interval is all values from 0 to infinity. We can put a round bracket on 0. Personally, I think a square bracket's more appropriate. But either way, you must have a round bracket on the infinity. That's the increasing interval. The decreasing interval is all x values less than 0. In other words, if x is any value in between negative infinity and 0, you're in a decreasing interval. And remember, don't look at that arrow. That's not telling you that it's increasing. That's just helping you understand the behavior of the graph. However, to determine if something is increasing or decreasing, what you do, recall that you want to go to a point on the interval, take a minuscule step to the right and ask yourself, do you go up or down? And if you go down when you take a minuscule step to the right, you're in a decreasing interval. Symmetry, this is an even function because it reflects upon itself in the y-axis. In other words, it's symmetric about the y-axis. As x goes to negative infinity, y is shooting towards positive infinity, and as x goes to positive infinity, y is also shooting towards positive infinity. There's our end behavior. Now let's talk about the cubic function. We can make a table of values of this function, and if we do, we have these values right here. Now, when we, actually there's some errors here. When x is -3, -3 quantity cubed is the same as -3 times -3 times -3. So that actually equals -27. So anyways, we have the values here as I've modified. And when we graph those on a curve, we see that on a Cartesian plane, we see the general behavior of the function. Now, we did not include the points -3, -27, and 327 in the graph I just showed you because we have to save room. And although it may not be obvious, this curve is actually infinitely wide to the left and right. Any x value to the far left or to the far right can be inputted into that function. And so what we want to remember is the basic behavior as we've shown there, as well as the three key points of -1, -1, 0, 0, and 1, 1. The domain of this function is all real numbers, and the range is all real numbers. And the increasing interval is all values from -infinity to infinity. Any x value between -infinity and infinity, if you insert it to the equation of the function, you'll end up at a point on the curve. If you then take a minuscule step to the right, you'll go up. Again, do not pay attention to the direction of that arrow. That's not telling you it's a decreasing function. That's just telling you where the points are. Remember, to be an increasing or decreasing interval, you're taking a step to the right, no matter where the direction of the arrows are in the function. Symmetry, this is an odd function because it has rotational symmetry about the origin. This red portion, if I rotate it 180 degrees, will fall exactly on the other side. End behaviors, as x goes to -infinity, so as x goes this way to the far left, y is going down. And as x goes to the far right, y is going up. So our end behaviors are as listed there. The reciprocal function. This is an interesting one because this curve has two asymptotes. An asymptote is a line that a curve approaches and gets infinitely close to but never touches. This particular curve has both a horizontal asymptote, the x-axis with the equation y = 0, and a vertical asymptote, the y-axis with an equation of x = 0. Now when we graph the curve, it looks like this. If we want to establish why it looks like that, we can plug in many different values for x and many different values for y. And if we plot all those points, we will see that this is ultimately the behavior of the function. Now, a few things are noticeable. The larger in magnitude the x value gets, whether positive or negative, the closer to 0 the y value gets, but the y value will never equal 0. Graphically, this means that as the function's x values get closer to -infinity or infinity, the y value will get closer to 0, but the y value will never equal 0. This means that the line y = 0, i.e. the x-axis, is a line that the curve will approach but never touch. It is an asymptote, i.e. a horizontal asymptote. The x value can never be 0 because that would make the denominator 0. Remember, the function is y = 1 over x. If I let x = 0, the denominator is 0. We can't allow that. So that means the x value can get infinitely close to 0 from either the left or the right. The line x = 0 ends up being a vertical asymptote. The larger in magnitude the x values get, the smaller in magnitude the y values get. The smaller in magnitude the x values get, the larger in magnitude the y values get. So putting all those ideas together, we get the curve that we showed you here. This is the parent function. And it's important to remember the basic behavior of the function as well as 2 points, -1, and 1, 1, and also know the horizontal asymptote y equals 0 and the vertical asymptote x equals 0. Now, our domain and range, our domain is x less than 0, x greater than 0, or kind of a clever way of expressing that is just saying x is a real number such that x doesn't equal 0. Our range is y less than 0, y greater than 0. Equivalently, we can write our range this way. Now, our increasing intervals, we have none. There's no point on this curve where if you took an infinitely small step to the right, you would go up. However, our decreasing intervals, we have actually 2 of them. This is a decreasing interval because anywhere on there, if I take a step to the right, I go down. And similarly, the portion on the right-hand side above the x-axis, that is also a decreasing interval. So if I state that in interval notation, I can say negative infinity to 0 in union with 0 to infinity. Now, we do not say negative infinity to infinity is a decreasing interval because at x equals 0, there is no point. And so therefore, we can't say x equals 0 is part of a decreasing interval. So it would be wrong to write that. Symmetry. This is an odd function because it has rotational symmetry about the origin. If we rotate that curve 180 degrees around the origin, it will fall back onto itself. As x goes to negative infinity, y gets infinitely close to 0. So as x goes far to the left, y keeps getting closer to 0. And as x goes far to the right, y keeps getting closer to 0. So our end behaviors are as written. Now let's talk about the exponential function y equals 2 to the x. It's important to recall this from last year. And y equals 2 to the x looks like this. The farther we go to the left, the smaller the y value becomes. However, the y value will never be 0. The x-axis is a horizontal asymptote. So our domain is x is an element of the reals. Our range is y is an element of the reals such that y is greater than 0. Our increasing interval is all real numbers. We usually put increasing intervals in interval notation as I indicated. There is no decreasing interval to this function. This function is neither even nor odd. It does not reflect exactly upon itself in the y-axis, and if we were to rotate it 180 degrees about the origin, we'd end up with a curve below the x-axis. It definitely is not rotationally symmetric about the origin, so it is not odd. The end behaviors, as x goes to negative infinity, y goes to 0. As we go far to the left, y gets closer and closer to 0. And as we go far to the right, y gets infinitely high, so y goes to infinity. Now, the exponential function 3 to the x is very, very similar to 2 to the x in a lot of ways. Different values, but a lot of the same general behavior. The farther we go to the left, the smaller the y value becomes, but it will never be 0. Y equals 0 is a horizontal asymptote. Our domain and range are the same as they were for 2 to the x. And our increasing interval is the same, and we have no decreasing interval. For the same reasons, the function is neither even nor odd, and we have the same end behaviors we had for the function 2 to the x. Now let's look at the exponential function y equals 1/2 to the x. We could make a table of values if we wanted, and if we do that, we get the curve as shown right there. The farther we go to the right, the smaller the y value becomes, but it will never be 0, so the x-axis is a horizontal asymptote. The domain is all real numbers. The range is all real numbers greater than 0. Now here's where it gets a little different. There's no increasing interval like there was for the other 2 exponential functions. Rather, it's all decreasing. As we take a minuscule step to the right, we'll be going down at all times. So the interval notation description of the decreasing interval is x element of negative infinity to infinity. The function's neither even nor odd. As x goes to negative infinity, y shoots up to positive infinity, and as x goes to infinity, y shoots to 0. We can look at the exponential function y equals 1/3 to the x. Looking at that, we would come up with the table of values that we have shown. The function looks similar to 1/2 to the x, but it's a little steeper. The farther we go to the right, the smaller the y value becomes, but it will never be 0. The x-axis is a horizontal asymptote, and so we get the domain and range as shown right there. There's no increasing interval, and the decreasing interval is all values between -infinity and infinity, for similar reasons as we had for the last exponential function we just looked at. The function's neither even nor odd. It's not symmetric about the y-axis, and it's not rotationally symmetric about the origin. And just like the function y equals 1/2 to the x, the end behaviors are as x goes to -infinity, y goes to infinity, and as x goes to infinity, y goes to 0. Now, let's recall a couple of trig functions. The sine curve. The curve y equals sine x has the following points in degree mode, and it looks like this. Of course, that's only one cycle of the periodic function. The function actually goes infinitely in both directions. Recall from grade 11 that the amplitude is 1. Amplitude is a measure of the height from the axis of symmetry to the highest point. So that's 1. Or you could say from the axis of symmetry to the lowest point. That's 1 as well. The axis of symmetry is the straight line that the function is going equally above and below. The phase shift is 0 because that indicates how far from the origin we moved. Well, the parent function starts at the origin, so the phase shift is 0. And the period is 360 degrees. A period is the horizontal length of one complete cycle. So in other words, how long is it horizontally to complete one cycle? And we see there that the period is 360 degrees. In radian mode, it's very similar. We just convert to radians using the idea that 180 degrees is equal to pi radians. Now, we are going to have an extensive trigonometry unit later in the course, but right now we're talking basics here. Now, that's only one cycle of the periodic function, but you might recall from grade 11 that similar to what we just said, the amplitude is 1, the axis of symmetry is at y equals 0, the phase shift is 0, and the period is 2 pi. Now, the domain is x element of the reals because any real number can be plugged in for the angle of a sine x curve. The range is all values between -1 and +1. Now, we're going to take a look at what this curve looks like when we actually extend it out in both directions. The curve y equals sine x looks like this. And it goes on infinitely to the left and infinitely to the right. Okay, many different periods. Now, if I said to you, what are the increasing intervals of this curve, you'd say, okay, well, it goes from an x value of -90 degrees to an x value of 90. And then it goes from an x value of 270 to an x value of 450. And it goes from an x value of 630 to an x value of 810, just like we've written here. Or if you prefer to not instead of saying -90 less than or equal to x less than or equal to 90, as we discussed in one of our other slides, you can say -90 degrees less than x less than 90 degrees. I actually prefer that you put the equal sign in there because I think the definition supports that. But your textbook says does not include the equal sign, so the textbook only says less than, so I'll accept either. But anyways, we could say that those are the increasing intervals. And by giving 3 of them, we're saying there's a pattern going on here. And by putting dots on the far left and dots on the far right, the way we've done here, we're indicating that it goes infinitely in both directions. And we're saying to the reader, look at the pattern and you'll figure out what I'm trying. Okay, and we had a little break in the video. But as we said a minute ago, by putting these dots here, you're telling the reader to look for the pattern, and it goes in both directions. That's for increasing intervals in set notation. We could also do it in interval notation, of course. And just like we had negative 90 degrees less than x less than 90 degrees, we can put that in interval notation using round brackets. Or if we choose to use less than or equal to, then we should use square brackets. And as I've mentioned before, I believe the definition warrants using square brackets, because I believe the definition of increasing intervals implies you include that one at the top, but your textbook disagrees, so I'll accept it either way. But if you're going to be using less than or equal to in your set notation description, it makes sense to use square brackets in your interval notation description. And if you're just going to be using less than in your set description notation like the textbook does, then it makes sense that you would be using round brackets in your interval notation. And there's no brace brackets here when you're in interval notation. There's no brace brackets on the ends, but you do still have the dots going in both directions. Should be a comma there. But you've got the dots going in both directions, x element of, and that lets the reader know that there's a pattern going on in both directions. Here's one increasing interval, here's another increasing interval, here's another increasing interval, etc. Okay, now we could of course put all those intervals into radian mode by converting all degree measures with radian measures, and you might recall that 90 degrees is equal to pi over 2 radians. For decreasing intervals, very similar process would occur. Negative 270 degrees is right here, and negative 90 degrees is right here. That's a decreasing interval because it goes down to the right. And so we could put the less than or equal to signs, or as your textbook does, the less than signs. And again, very similar to the other, to the situation we just dealt with the increasing intervals, we want to establish a pattern. And so putting 3 of these increasing intervals really helps solidify what that pattern is, and putting a dot, dot, dot on the left and the right is an appropriate way to go. If you want to think of it like the textbook thinks of it, then you won't put the less than sign in the, you won't put the equal to sign when you state your decreasing intervals. Or you could, if you think of the definition the way that I do. Okay, there's your decreasing intervals. Similarly, in interval notation, we could write it out this way, like it's stated before. There should actually be commas here. I've made that mistake a couple times. There should be commas there, just like there is here and here. Should have commas. Okay, then we could put all of that into radian mode by converting all degree measures with to radian measures. And now let's look at symmetry. This is an odd function. It might be a little bit difficult perhaps to see that, but if we were to take this first hump here, we'll call it, and if we were to rotate that 180 degrees about that origin, rotate it 180 degrees, you would end up perfectly with this hump down below. And if you did the same thing with this one, rotated that 180 degrees, again about the origin, it would end up exactly here. And so what we see is that this entire right half of the curve can be rotated 180 degrees onto the left half of the curve, and similarly the left half of the curve could be rotated 180 degrees onto the right half. It's an odd function. And if you recall, algebraically what that means, odd functions, it always means that f at negative x is equal to negative f of x. So looking at the graph, we see that it actually means that sine of negative x is equal to negative sine of x. And that's something we're going to go into in the trigonometry section of this course much more. For end behaviors, we see that there's no, this curve definitely doesn't go to infinity. I can't say that that curve shoots off to infinity because it doesn't. It's always fluctuating between -1 and 1, but I also can't pinpoint a number in either direction that the curve actually goes towards. A limit, as we'll talk about in the calculus course. I can't really set that down, and so what we do is we say there are no discernible end behaviors. And as we get into, when we eventually take calculus, what that'll mean is that the limit as x goes to negative infinity of this curve does not exist, and the limit as x goes to positive infinity of this curve does not exist. For now, though, we'll just say that as we go this way, there's no discernible end behavior. It's fluctuating too much. And as we go that way, similarly, no discernible end behavior. All right, now we can talk about the coast curve. There's going to be some similarities here. You may recall the coast curve has the points shown, and when we graph them, it looks like that. Now, that's only one cycle of a coast function. You might recall it goes infinitely to the left and infinitely to the right. The amplitude of this curve is 1. The axis of symmetry is y equals 0. This curve spends as much time above y equals 0 as it does below y equals 0. And the amplitude is 1 because that's the vertical distance from the axis of symmetry to the highest point. When we're at the initial, when we draw the initial cycle of this, that we say the phase shift is 0 because the x value of that first point is 0. And the period of this is 360 degrees. What that means is if we go 360 degrees, we get to the end of one cycle, and then we'll repeat it with the next cycle. We could also put the coast curve in radian mode. It would look like that. Remember, pi over 2 radians equals 90 degrees. And it goes infinitely in both directions. Instead of saying that the period is 360 degrees, we can say the period is 2 pi radians, which is the same thing. Our domain is x element of the reals because, as we've said, this curve will go infinitely in both directions. And our range is the only possible y values are those between -1 and 1 inclusive. Okay. Now, to do increasing intervals, very similar to the way we did them with the sine curve, we will draw the curve heading in both directions. We'll say this is an increasing interval right here from -540 to -360. When x varies between -180 and 0, we have another increasing interval. When x varies between 180 and 360, we have another increasing interval. And so we see the pattern there by stating 3 of them. We've really set down what that pattern is, and by putting the ... in each direction. When you have 3 dots in a row like that, it's called an ellipsis. By putting an ellipsis on both sides, we've established there's a pattern we're looking at. And you can put less than or equal to, which I think is correct according to the definition of increasing intervals, or you can take the approach that the textbook does and just put less than signs there. If you're going to take the approach the textbook does and put less than signs, it makes sense to use round brackets like we're doing right here. If you're going to take the approach that I generally do, and again, I'll accept it in both ways, but if you're going to take the approach that I generally do and use less than or equal to signs, then you should use the square brackets when using the interval notation, because when you use less than or equal to signs, that implies square brackets. Okay, and when you use just a less than sign, that implies round brackets. Okay, so we could also put those into radian mode, and now we could talk about decreasing intervals. For decreasing intervals, one decreasing interval is right there, another one is right there, another one is right there. And so we could say -360 to -180, 0 to 180, 360 to 540, and we would have our decreasing intervals. And as I've mentioned many times, you can think of it, you can have the philosophy of including the value of -360 or -180, etc. in your decreasing interval, or you could use the textbook's philosophy and not include them. And if you're going to use the textbook's philosophy of not including those, you'll put round brackets on your interval notation. If you're going to use what I think is the more correct philosophy, you'll put square brackets in your interval notation. And we could do this in radian measure as well, of course. Now let's talk about symmetry. For symmetry, this is kind of interesting. This is not an odd function like the sine curve was. This is an even function. If you were to reflect this piece right there in the y-axis, you would exactly get this piece, and vice versa. If you were to reflect this piece right here in that y-axis, you would exactly get this piece, and vice versa. This curve's a perfect reflection in the y-axis. That makes it an even function. And if you recall, an even function is a function in which f of negative x equals f of x. So what that means, since cos x is an even function, we can tell by looking, that means that cos of negative x will equal the cos of x. And again, we'll go into that in more detail when we do our trigonometry section later. Our n behaviors, for the same reasons as sine had no discernible n behaviors, the cos curve has no discernible n behaviors. And we're at the end of our discussion.